Hello and welcome to today's lesson on using wavefronts to represent refraction. In today's lesson, we will learn what wavefronts are and why they are useful. We will then illustrate refraction with wavefront diagrams. So far, you are familiar with the concept of refraction and its associated ray diagrams. You understand how light bends when it travels from one medium to another, like from air to water, and how we use ray diagrams to represent this behavior. Building on this foundation, we will now explore how wavefront diagrams provide an alternative and insightful way to visualize refraction. Let's get started. To start, let's get a clear understanding of wavefronts. Imagine you're looking at waves in the ocean. If you take a snapshot at any given moment, the highest points of the waves, which are the crests, can be connected with an imaginary line. This line is what we call a wavefront. Essentially, wavefronts are lines that represent the crests or high points of waves at a particular instant. They help us visualize two critical aspects of waves, their direction and speed. In terms of direction, wavefronts show us how the wave is moving. The wave propagates perpendicular to these wavefronts. As for speed, the spacing between consecutive wavefronts indicates the wavelength. If wavefronts are spaced closely together, it means the wavelength is short and vice versa. Let's look more at how wavefronts can help us understand refraction. As we have learned, when waves travel from one medium to another, such as from air to water, their speed and direction change, known as refraction dot. We often use ray diagrams to represent this, but wavefront diagrams can give us an insightful alternative view. Let's do a step-by-step illustration of a wavefront diagram. Begin by drawing several parallel lines on a piece of paper to represent wavefronts in the first medium, for instance, air. These lines should be evenly spaced, indicating a constant wavelength. The wavefronts are straight and parallel, showing that the wave is propagating uniformly. Now, let's introduce a boundary where the wave enters the second medium, such as water. Draw a line at an angle to represent this boundary. As the wavefronts hit this boundary, they change speed and direction. Next, we need to show the change in speed and direction. If the wave is moving from a less dense medium to a denser medium, it slows down. When the wave slows down upon entering the second medium, the wavefronts get closer together. The key here is that the spacing between the wavefronts decreases, indicating a shorter wavelength. Conversely, if the wave is moving from a denser medium to a less dense medium, it speeds up. The spacing between the wavefronts increases, representing a greater wavelength. The wavefronts bend away from the normal line in this case. To represent this bending, draw the wavefronts in the second medium, keeping in mind the change in spacing. If the wave is slowing down, the wavefronts will bend towards the normal line. If the wave is speeding up, the wavefronts will bend away from the normal line. Finally, add arrows to your diagram to show the direction of wave propagation before and after the boundary. In the first medium, the direction is straight towards the boundary. Upon entering the second medium, the direction changes according to the refraction rules. We know it bends towards the normal if slowing down, and bends away if speeding up. Wavefront diagrams are a powerful visual tool that can help us better understand the subtleties of refraction. By observing how wavefronts change in spacing and direction at the boundary between two mediums, we gain a clearer picture of how waves behave when they undergo refraction. In today's lesson, we delved into the use of wavefronts to represent refraction. We began by understanding wavefronts as imaginary lines connecting the crests of waves, which help visualize wave direction and speed. We then explored how wavefronts change when waves travel from one medium to another, illustrating the concept of refraction. We used diagrams to represent these changes, adding arrows to indicate the direction of wave propagation before and after the boundary. This visual tool provided a clearer understanding of the behavior of waves during refraction, complementing the traditional ray diagrams. Watch the rest of the GCSE Physics course at Sophos Education.